physics course, the topic, one-dimensional kinematics, this section, 2.7, is specifically your first introduction to acceleration. But one thing I would also like to do in this section is make sure that I explain very clearly the differences between velocity and acceleration so you don't mix the two of them up as we move through the course. To reiterate from an earlier video, because it's so important, the three basic ways in which the motion of matter can be described would be: the matter is not moving, it has zero velocity. Matter that is not moving is said to be at rest or stationary. Matter that is moving the same distance every second is said to be moving at a constant velocity. So he's not going faster or slower, he's moving at the same steady pace. Now, acceleration, or constant acceleration, matter that is undergoing constant acceleration, is either increasing its speed or velocity, decreasing its speed or velocity, or changing direction. Now, in just a second, I will reiterate, because it's very, very important that you understand that acceleration means three different things in physics. There are three different ways in which an object can be said to be accelerating. One of the most important concepts that must be made clear early in the physics course is that acceleration does not just mean going faster and faster. Since acceleration is simply a change in velocity, and velocity is a vector made up of both magnitude and direction, changing the velocity can mean increasing the velocity, or you could just say increasing the speed, or decreasing the speed or velocity. In either case, it is changing. The magnitude, the number, is changing. It's either going up, getting faster, or going down, getting slower. Now, the other way to change a vector, like velocity, is to change its direction. So acceleration, since it's a change in velocity, can mean that you are simply changing the direction. Now, in the next second, I'm going to be giving some examples of increasing speed, right? Acceleration where the speed of the object is increasing, acceleration where the speed of the object is decreasing, and acceleration where the speed of the object is staying the same, but the object is changing direction. Now, keep one other thing in mind. Many physics teachers do not use the word deceleration because it's unnecessary. Deceleration, meaning slowing down, is a form of acceleration. You know from the context of the question, when you say acceleration, whether you're going faster, going slower, or changing direction. So the word deceleration becomes unnecessary, although it's perfectly acceptable to use it when you're slowing down. Here are some examples of each of the three types of acceleration. If you are increasing velocity, one example would be a child on a bike, and the child is moving at a certain slow speed, and then a dog starts chasing the child, so the child pedals faster. The child has just increased his or her speed, or increased his or her velocity. If somebody drops a rock, when they first drop it, the speed of the rock is zero. You just let it fall. All right, so in the beginning, it's not going at all. When you first let it go, the velocity is zero. All right, that means dropped from rest. As the rock or the object falls, it goes faster and faster. The earth is pulling it down faster and faster. So the speed increases, or you could say the velocity increases as it's going down. What about decreasing velocity? If a taxi driver is going at a certain speed and the taxi driver sees that the light ahead is yellow, the taxi driver gently puts his foot or her foot on the brakes, and the car starts to slow down. The speed decreases, or you could say the velocity of the car decreases. And then right before the red light, right before the crosswalk, the car slows to a complete stop. The car comes to rest. What about if somebody throws something straight up into the air? A bride has all of her ladies, her lady friends around her, and she throws the bouquet straight up into the air. Well, but the Earth is pulling it down. So what happens is it goes slower and slower and slower until it gets to a certain height and it stops. Briefly. Now we know it's going to fall back down again, but what was happening on the way up is it was slowing down. It was decreasing velocity. So speeding up is a form of acceleration. Slowing down is a form of acceleration. And here's the last form of acceleration, changing direction. A car on a curve, for example. Now the car could maintain a speed, if it's a very fast car, it could maintain a speed of 30 meters per second all the way around the curve. But the direction is constantly changing. And again, since acceleration is a change in velocity, and velocity consists of both a magnitude, which is a number, and a direction, that means that by changing the direction, you are changing the velocity. You are, by definition, accelerating. What about if you are giving some exercise to your pet hawk, and you put a little piece of meat with some feathers on a string, and you swing it around your head so the hawk can chase it? Well, you can swing it around your head at a constant speed, or a constant, you can swing it around your head at a constant speed, but because the direction is constantly changing, the velocity is changing as this hawk lure is going around your head in a circle. This is kind of how you exercise your pet hawk. When you exercise your dog, you take a ball or a stick and you throw it, and the dog fetches and brings it back to you. Well, if you want to keep your hawk flying around and getting exercise, you take this little piece of meat with some feathers on it, and you put it on the end of a big long string, and you swing it around your head, and the hawk keeps chasing it, and your pet hawk gets exercise. Now, we are not going to talk about these changes in direction anymore, because we will talk about this in a ton of detail in the forces topic in the video called centripetal force. So, the types of acceleration we're going to talk about for the next couple of videos or so is going to be either increasing velocity or decreasing velocity. We'll talk about things that go around in circles when we talk about forces in the section called centripetal force. It's very important that when you see the word rate, that you understand that it is anything that is divided by time. Now, both velocity and acceleration are rates. Let's look very quickly at an example of an equation for velocity. All right, velocity, I'm going to put displacement divided by time. And again, you simply look, velocity is this divided by time. Since it's divided by time, velocity is a rate. All right, acceleration is also a rate. Here's a change in velocity, and here's the time on the bottom. So because it's divided by time, acceleration is also an example of a rate. All right, now, just for the heck of it, all right, here's power. All right, you'll be doing power much later in the physics course, but power is going to be work divided by time. So again, power is a rate. Now, you could also use this to come up with a sort of a definition for each of them. All right, velocity would be the rate at which displacement changes. Acceleration would be the rate at which velocity changes. All right, and power would be the rate at which work is done. So you see what a rate is. The first thing I'd like to do to distinguish zero velocity from constant velocity and constant acceleration is to mark the motions of, let's say, 3 people on a number line. We'll start with somebody who has zero velocity, somebody who's just standing still. All right? We're going to put that person at 0. And they're going to stand there. They're not going to move. Now, we're going to record 3 seconds, and each dot is going to be another second. Now, of course, the person who's just standing there, the dots are all going to be on top of each other. So if we start there, and after 1 second, the person is still standing in the same place, and after 2 seconds, the person is still standing in the same place, and after 3 seconds, the person is still standing in the same place. This shows that the person did not move in 3 seconds. Now, what about a constant velocity? The same exact change in position or displacement every second. We'll start the person here. All right, let's do this person actually in blue. So this person starts here at 0. And after 1 second, the person is now at 2 meters. And after another second, now the person is at 4 meters. This person is going 2 meters every second. He's not going faster. He's not going slower. He's going at the same constant velocity. That's why these are evenly spaced. And after the 3rd second, all right, he's going to be at 6 meters. Now the spacing here should be perfect. I did draw these lines, so it's off a teeny little bit. But the spacing should be perfect. If you have a piece of graph paper, you can do this perfectly. All right, so now what if the person goes, we're going to use for acceleration faster and faster and faster. One type of acceleration. So we'll start the person here at 0. Then in the 1st second, the person covers 1 meter. But since the person is going faster and faster, in the next second, the person covers more than just 1 meter. This time the person covers 3 meters. The person was here, now the person is here, and they covered in 1 second 3 meters. Now the person is going faster, the person is accelerating. He's still going faster, so he's going to cover even more distance in the same 1 second, in the same amount of time. So between this is second number, this is 1 second, 2 seconds. So in the 3rd second, all right, the person is going to cover, let's see, we're at 4, 5, 6, 7, 8, 9. The person goes up to here. All right? So I hope you can see that when the person is increasing their velocity, they're going to cover a greater distance in the same amount of time. All right, the person is going slowly here, then faster, then faster. This person is traveling at the same constant velocity, 2 meters, then 2 meters, then 2 meters. This person is not moving at all. All right, so you can see how these dots can represent different types of motion. 0 velocity, he's not moving. He's staying at 0 meters. 0 meters, 0 meters, 0 meters, 0 meters. This person, all right, is going 2 meters every second. So he's at 0, then he's at, I'll count the seconds on my fingers here. He starts at 0, now he's at 2, now he's at 4, and now he's at 6. So every second, he went 2 meters. This person started out slowly at 0. In the 1st second, they went to 1 meter. Then they covered more distance in the next second. They covered 3 meters in the next second. And they're still going faster again. So this time, they covered 5 meters in the next second. Right? So this is on a number line. Now you'll see these dots in other situations. When the dots are evenly spaced, that's going to represent constant velocity. When the distance between the dots is changing, the person is either increasing velocity, as in this case. If the spacing is getting smaller, then the person would be decreasing velocity. All right? So we'll go on and do some more things. Now, let's see what 0 velocity, constant velocity, and constant acceleration look like on displacement versus time graphs. Now you could also call this, for right now, you could call it a distance versus time graph. You could also call it a position versus time graph. At this point, it doesn't really matter. Now, the y-axis in each case is going to be displacement. So let's label that over here, displacement. And the unit for displacement is going to be the meter. The x-axis for each of these graphs is going to be time, and the unit for time is going to be the second. We have here 1 second, 2 seconds, 3 seconds. All right, 1 second, 2 seconds, 3 seconds. We're going to use the same data that we put on the number lines just a moment ago. 1 second, 2 seconds, 3 seconds. And on the y-axis, all right, displacement, 0 meters, 1 meter, 2 meters, 3 meters, 4, 5, 6, 7, 8, 9, 10. Okay? So, when the person was standing still, all right, the person was standing at 0 meters. All right, so we put right here, he was standing at 0 meters. All right, he was still standing at 0 meters here after 1 second. After 2 seconds, he was still standing at 0 meters. After 3 seconds, he was still standing at 0 meters. So right here we have a flat horizontal line is what zero velocity looks like. I'm making it a little thick there. What zero velocity looks like on a displacement time graph. That is zero velocity. Remember, this is a displacement time graph. The y-axis on all three of these is going to be displacement. Now, keep in mind that zero velocity, the person could be standing, for example, let's say the person was standing at 6, all right? He's standing at 6, he's standing at 6, he's still standing at 6, he's still standing at 6. I want you to remember that zero velocity on a displacement time graph does not have to be at 0. The person could be standing someplace else as long as they're not moving. All right, he's not leaving this 6 meter mark. All right, that's still showing zero velocity. All right, so zero velocity on a displacement time graph is a flat, horizontal line. All right, a horizontal line. Flat and horizontal are synonyms, okay? It's redundant. Now, what about constant velocity? And we had that person in blue, so let's do that person in blue again. That person started at 0 meters. Then after 1 second, the person was at 2 meters. After 2 seconds, that person was at 4 meters. And after 3 seconds, that person was at 6 meters, right about there. Okay. So, what we have there is a diagonal, right? It is a straight diagonal line, okay? Trying to make it nice. All right, it's not perfect, but you get the idea. All right, so we've got a diagonal line, shows constant velocity on a displacement time graph. All right, so let's say a diagonal line. A diagonal line shows constant velocity on a displacement time graph. Now, what happens when we plot the same points that we had on the number line just a moment ago for constant acceleration? When the person started, the person was at 0. At 0 time, the person was at 0 displacement. Then at 1 second, the person was at 1 meter. Right? Then at 2 seconds, the person was at 1, 2, 3, 4 meters. So that's about there. Okay? And then at 3 seconds, the person was at 9 meters. So again, these are the meters here. You see the y-axis is meters. So that's 4, 5, 6, 7, 8, 9. So 9's right there. There's the 3. That should be right about there. Okay. Now, you can see very clearly that this is not a straight line. All right, there's no way. See how that one's all up there like that? There's no, if you try to make these even, then those two are in the wrong spot. Try to make all three of these sort of even. This guy's too low, that guy's too high. There's no way that this is a straight line. This is a curve. Acceleration, constant acceleration on a displacement time graph is going to look like a curve. Okay, so now let me try to make this really nice. Just a nice swing. There we go. Perfect. Okay. Beautiful curve. All right? So, what have we learned here? All right, what you want to take away from this. and this is a curve. Okay, let's call this an exponential, all right, an exponential curve, all right, or a curved line, okay? So what you've learned here, all right, is that zero velocity on a displacement time graph is a horizontal line. Constant velocity on a displacement time graph is a diagonal line, a straight diagonal line. And constant acceleration on a displacement time graph is an exponential curve. It is a curved line. So now, when your teacher asks you, what does it look like? You can't say, oh, it's a line. Because what we want to know is, do you mean a horizontal line, do you mean a diagonal line, or do you mean a curve? Okay, so you have to be specific. All right? Moving right along. Again, what's the difference between constant velocity and constant acceleration? Well, a constant velocity of 2 meters per second means that your distance is changing 2 meters every second. Now, let's go with 4 seconds, okay? Similar to what we did with the number line and the graph, but we'll do 1 extra second just for fun. All right, so the time is going to be 0, 1, 2, 3, 4 seconds, okay? Now, if you have a constant velocity, that means you have no acceleration. You are not accelerating. So your acceleration is staying at 0. If you have a constant velocity, you are not accelerating. What is your velocity? Well, your velocity is constant. It's 2. Right? So your velocity is 2, 2, 2, 2, 2. Now what about your distance, right, or your displacement? Well, if you start at 0 and you go 2 meters per second, 2 meters every second is the change. Then after 1 second, you're at 2 meters. After 2 seconds, you are at 4 meters. After 3 seconds, you are at 6 meters. And after 4 seconds, you are at 8 meters. So look at this. Time is going by. Your acceleration is 0. Your velocity stays at 2. What's changing is your distance or displacement. Now, look at a constant acceleration of 2 meters per second per second. 2 meters per second per second. That's why the unit for acceleration, all right, is 2 meters per second squared. 2 meters per second squared. Because what's changing, when you have an acceleration of 2 meters per second, your velocity, 2 meters per second, is going up every second. So your velocity is going to change every second. You see how the meters per second is changing per second? Your velocity is going to go up 2 meters per second every second. So let's see how that pans out over here. Time, acceleration, velocity, displacement. Your time again, 0, 1, 2, 3, 4. Your acceleration is a constant 2 meters per second squared. 2 meters, it's a constant acceleration. Your acceleration stays at 2, all right, at 2, at 2. A couple different ways to write the number 2, that's okay. Now, your velocity, let's say, is initially 0. After 1 second, your velocity is now 2. After 2 seconds, your velocity is now 4. Your velocity is going up every second. See here, your velocity is staying the same. Your distance is going up by 2 meters every second. But here, your velocity is going up by 2 meters per second every second. So now after 3 seconds, your velocity is 6 meters per second. And after 4 seconds, your velocity is 8 meters per second. All right, now needless to say, if I had a little more room here, I'd put all my units up here. Time is seconds, acceleration meters per second squared, velocity is meters per second, displacement is meters. Seconds, meters per second squared, meters per second, meters. Now, what about the distance or displacement? It's not going up by an even 2 every time, because you're going faster and faster. So if we start with a displacement of 0, right, after the first second, you've gotten to 1 meter. Then after the next second, you've gotten up to 4 meters. After the next second, you've gotten up to 9 meters. And after 4 seconds, you are at 16 meters. Now, just for the heck of it, all right, look here. All right, your change in distance here is 2. All right, your difference is 2. Your difference is 2. Your difference is 2. Look at how it's changing over here. Here it changed by 1. Here it changed by 3, right? Here to here it changed by 5, and here your distance changed by 7. All right, so your change in distance is increasing, right, exponentially. It's not this even 2, 2, 2, 2, 2. It's going up. All right? What's going up evenly when you do an acceleration is your velocity. Your velocity went up 2 meters per second, then up another 2 meters per second, then another 2 meters per second, then another 2 meters per second. All right? You may want to come back to this chart in a week or two. This chart is going to make a little bit of sense right now. It's going to make a lot of sense maybe a week or two from now, and a whole bunch of sense when you get really into the course, maybe a couple of months. All right, there's a lot going on these two fairly simple looking little charts. Now, the last thing I'm going to be showing you in this video is a skill that you're going to use for the entire year with many, many different equations, right, and many, many different definitions. Now, I'm still going to be showing you, as an example, the difference between velocity and acceleration. But, as I said, this skill is going to apply to all the equations you're going to learn all year long. You need to be able to do 3 things with every equation. You need to be able to take the equation, the mathematical equation, and turn it into an English sentence. You need to be able to take the English sentence and turn it into an equation. And you need to be able to derive, and the word derive means figure out, the correct unit based upon the equation. All right, so let's get into that. Now, the equation for velocity, right? Velocity is going to be a change in position or displacement. All right, so there's change is the little triangle, change in position with respect to time, or a change in position divided by a change in time. Now, let's figure out the correct unit for velocity based upon this equation. All right, the unit for distance or displacement, all right, is the meter. So the meter is going to be on top. Now, it doesn't matter if it's meters minus meters. Meters minus meters is still meters. Okay, 6 oranges minus 2 oranges is 4 oranges. When you subtract unit, the unit stays. All right, so it's going to be meters on top and seconds on the bottom. All right, there's your unit for velocity. Your unit for velocity is meters per second. When you see the dividing line, you say per. So this is meters per second. The unit for velocity is meter, for speed and velocity, is meters per second. All right? So, and when we get up to acceleration, I'll show you how to get the unit for acceleration. And you're going to be doing this all year long with all different units and all different equations. All right, now, change in displacement, what that means is the final displacement minus the initial displacement. Change in time is going to be the final time minus the initial time. Now, generally speaking, your initial displacement is going to be 0, almost 90% of the time. And 90% of the time, your initial time is going to be 0. When that's the case, then this equation is very, very simple. It simplifies down to velocity is going to be equal to, right, displacement divided by time. Right, that would be d final over t final. But since we're not worried about the initial, because in this case they're both 0, we don't need the subscripts. All right, so there's your equation for your definition of velocity. Now, how do we take this equation here, all right, and change it into an English sentence? All right, here we go. velocity is, right? Velocity is. See, equals means is, right? Now, a measure of, I'm just throwing in some words here. All right, a measure of. Now, you see time on the bottom, so you know it is a rate. All right? So velocity is a measure of the rate of change of position. You can say position or displacement. All right? Of an object. So now, you said that it's a change in position. There's the change in position. You said that it's a rate. The time on the bottom is the rate. So you took everything about that equation and translated it into English. Okay, watch again. Velocity is, right? Velocity is, okay, a measure of, right, the rate of change of position. Rate means you're dividing by time, okay? Change of position is your change of position on top here. All right, so you're dividing by time and it's a change in position, all right, of an object. Okay, so you can take the equation, turn it into an English sentence. You can take this English sentence and turn it back into an equation, all right? Now, what's changing here is your position or displacement. The position or the displacement is changing. If it's a constant velocity, it's changing by the same amount every second. For example, 2 meters per second. We did this just a moment ago with that chart. All right, if your velocity is 2 meters every second, then you're going, I'll count the seconds with my finger, all right? You're going from 0 to 2 meters, to 4 meters, to 6 meters, to 8 meters, to 10 meters. In 5 seconds, you would go 10 meters. You're changing your position from 0 by 2 meters, all right, every second. So that's the equation which defines velocity, and also how to figure out the unit for velocity, right, and what velocity means. Your displacement is changing by the same amount every second. Your velocity, your speed, is not changing. You're not going faster, you're not going slower. This is constant velocity. So the last little thing that we're going to do here is talk about the equation which defines acceleration and how to derive the unit for acceleration, meter per second squared. Keep in mind, again, that acceleration can be, right, increasing velocity, decreasing velocity, or changing direction. And I will use increasing velocity as the example right now. I'm not going to get into changing direction, because we will go over changing direction in all kinds of detail in the forces topic under centripetal force. So I will mostly be talking right now about an increasing velocity. Keep in mind, acceleration can be speeding up, slowing down, or changing direction. Okay, but I'm going to use one example right now. All right, so now, the equation that defines acceleration. All right, acceleration is a change in velocity per unit time. Per unit time. The unit is usually a second on the bottom. All right, a change in velocity per unit time, or you can say a change in velocity with respect to time. What this means, acceleration is going to be a final velocity minus an initial velocity over a final time minus an initial time. Most often, the initial time is going to be 0. So what this is going to boil down to is that the equation is going to be V final minus V initial over time. All right, if the initial time is 0 and the final time is 5 seconds, that means it took 5 seconds. You're going to put your 5 seconds right down here. Now, let's derive. Derive means figure out the correct unit for acceleration based upon the equation for acceleration. You've got velocity on top, so on top is going to be meters per second. The unit for velocity goes on top. Now, you put a line. There's the line. On the bottom is the unit for time. The unit for time is the second. Now, we need to clean this up. We can reduce this, simplify this. All right? So I'm going to take this guy, this S on the bottom is really over 1. I'm going to invert, right, 1 over seconds. I'm going to multiply bottom and top by 1 over seconds, right? Invert and multiply top and bottom. These cancel, and the unit becomes meters per second squared. Meters per second squared. So I used the equation to derive the correct unit for acceleration. All right? Now remember that this trick about using an equation to derive the correct unit, you're going to use it all year long. That's why we're doing it right now. Okay? Now, the other thing you want to notice is that what's changing here is the velocity. The velocity is changing. It might be increasing, it might be decreasing, right, per unit time. The direction could be changing, not getting into that right now. All right, now, changing the equation into an English sentence. All right, here we go. All right, acceleration is, okay, acceleration is, I'm just going to put in some words here, all right, a measure of, okay, to make that make sense, the rate. Now, how do you know that acceleration is a rate? It's the equation, whatever it is divided by time, all right? So it's the rate of change of velocity of an object. Okay? So, how did we translate this English sentence from this equation? Acceleration is a measure of the rate. See the divided by time? The rate of what? The rate of change of velocity. All right? The rate of change of velocity. So you can take the sentence and write the equation from the sentence. You can write the sentence from the equation. All right? You want to be able to translate back and forth from math to English, English to math. So when you see an equation, you understand the definition of what the equation is for. All right? And you want to be able to, again, distinguish between velocity and acceleration, because velocity is how much the displacement is changing, but acceleration is how much the velocity is changing, right? How many meters per second is it changing, look, per second. Let me also write that. Get rid of this for just a minute. That what acceleration is, all right, is how many meters per second, all right, per second. Right, on top is velocity, right, meters per second per second. That's why it's meters per second squared. And the way you would say this is meters per second squared. All right, meters per second squared is the way you say that, or meters per second is how you want to think about it. It's how the velocity, meters per second, is changing each second. Remember, if you have an acceleration of 2 meters per second squared, the velocity is changing 2 meters per second every second. In that case, the velocity is increasing, 2 meters per second every second, assuming you start from an initial velocity of 0. So your velocity is going to be 2 meters per second, then 4 meters per second, then 6 meters per second, then 8 meters per second, right? The case where your velocity is increasing. I hope you've enjoyed this video, and I'll see you in the next video.